it's kind of like we have an input, then it goes in the system, and then we get the output values. So we have more information.
Gracias. We'll start from there. All right. The other graph, and probably all the graphs in your book, will always start at 0 with something interesting. This one starts at 0 with stuff that I'm not interested in. So we move the axis over to here, and we call this the start of the experiment. This is just the initial conditions. The other one started at 0. This one doesn't start at 0, it starts at 7. The output is on this graph over here. So ignore all that stuff, except you're going to have to get what the average of this line is over here, not including this stuff, but in here where it's fairly steady, get the averages out. And then draw that curve and stop out here. And then expand that, and this might look more like the other one except for the noise. Is that the last slide? We want to get the parameters from that graph and the time domain so that we can use in the Laplace domain. So we're doing elementary time to Laplace conversion. You'll learn more about that shortly. So we're going to get 3 parameters from that in the time domain. So let's do this. Oh, there's the experiment I got. Oh, I wanted to show you this. Here's the graph of the experiment that I just showed you. Let's look at another one. Think about that one. It's useless. It's a useless experiment because before the step occurred, this did not reach steady state. And this is baloney over in here. So if you get an experiment that has a graph like that, ignore it and do a better one, possibly waiting until a longer time before you take the step. You have control of the initial step height, and the step size, and when the step occurs. Those 3 things are under your control as an experiment. So if you get something like this, you wasted your time, throw it away, and do another one with maybe a longer time before it takes a step. All right, so let's look at this. This is your week 3 step response testing description that's on the web. Tell me your team color over there.
Teal.
Teal. Well, both of you stand up and read in unison from here this whole paragraph.
To observe experimentally the time response of the output function of the system to a step function input. To observe the system's steady state gain, K, the system's response time, tau, and the system's dead time, T0, if any. To make the observations for a number of different values for the size of the input step function and the initial steady state values. To make the observations for a variety of system configurations, if appropriate.
Sweet. 2 classes. Any question on what that means? These are the 3 parameters that you're going to be looking for. The gain, steady state gain, which has the symbol K. The system's response time, which I told you we're going to call tau. And then there's something that wasn't even on that other graph. It's dead time. You remember that graph that I showed you that when the step went up, it didn't do anything for a little bit of time, and then it started going up, the output? You remember that? Say yes.
Yes.
That's called dead time. The gain is real simple. It's the change in the output height, units, divided by the change in the input height, units. Steady state in both cases. So here's some graphs, shows you what I'm talking about. Notice that the units of this are different from the units of this, so they won't, so this delta will be different from that delta because they're different units. If I ate 3 apples per day, you notice, let me rephrase that. If I ate 21 apples in a week, how many would I eat per day? 3 apples per day, if you want to do the units. If you just said 3, you're not giving me the units, right? So this thing that we're going to do has units. All right, so Alex, will you stand up and read this paragraph loud and clear? Can you read it?
Kind of.
You want it larger?
It's fine. The system takes a certain time to respond to the input step. A typical response curve is shown in figure 3.1b. From this graph, you can get the characteristics of the system: steady state gain, response time, and dead time. These are called the first order plus dead time, FOP, DT, parameters of the system.
That's excellent, Alex. Are you Alex or Alexander?
I'm Alex.
Okay, the other one's Alexander sometimes and Alex sometimes.
I guess so.
Okay. All right. So here's procedures, lab assignments, results. Now, shall I click on this and show you what it is? Here's a web page that illustrates this fit. This fit that I'm talking about, we call fit 2 for reasons that I may or may not tell you ever. Shall I click on that and see what happens?
Yes, please.
Here is an experiment. And if you click here, you get the Excel graph that makes this. But here's the step occurred here at 50 seconds. Here's the input over on this side. Here's the output over on this side. The input goes from 40 up to 60, so that should be a delta. That's the change of the input. The input we call manipulated variable. That's the thing that comes in this side of the box. So this goes from 40% to 60%, so the delta is 20. Everybody say, I see that. Tell me your name.
Philip?
Philip?
Yes.
You saw that, didn't you?
Yeah, I totally saw it.
And all right, everybody say, I totally see it.
I totally see it.
Y'all are good. Then, here's the purple or pink or something, is the output curve over here. And it starts around 16 pounds per minute. This must be flow. And it goes up to 24 and a half. This says 8.2, so this must be a little above, whatever. So this delta here, delta of the output. C is the output. This is C over here, C, and this is M over here. Delta of the output is 8.2 pounds per minute. Can you see that? Tell me your name again. William. On the other side of you, William. Can you see that, William? And then the gain is delta C over delta M. I apologize for having D's in there. That's, whoever made this didn't do a very good job. That's the gain. .41, and it has units, just like apples per day have units. Pounds per minute are the units over here, over here. And percent are the units over there. So the gain, based on this experiment, is 0.41 pounds per minute per percent. How many of you ever heard of units like pounds per minute per percent before? Weird, huh? But that's what it is. If you have temperature, this will be temperature in degrees Celsius, I believe. So the gain will be temperature degrees Celsius per percent. If you have pressure, this will be centimeters of water. Sorry, I'm doing it backwards. This will be centimeters of water. So the units will be centimeters of water per percent. So that's the gain based on this experiment. That's one experiment to get the gain. And we have how many parameters that we want to get? 3. So here's the second one. It's called dead time. To do that, we draw a line, a straight line, wherever is the steepest slope of the output curve. This takes eyeball. This does not mean you go into Excel and ask it to tell you where the steepest point is. That's pain. Use your eyeballs. How many of you have at least one eyeball? Raise your hand. Y'all are good. Oh, turn that piece of paper over, Marion, and ask me and do the other thing.
Tell us about power failures.
Power failures. There was a power failure yesterday, right? Let me tell you about power failures and nature. When I was your age, in college, we didn't have personal computers. We had computers that sat in some room, secure room in a secure building, and we had to carry over stacks of cards with punched code in it. Put them in the window and go away and come back hours later, and we'd come back and we'd say, have you run my job yet? And they'd say, no, it'll be another 15 minutes. So you go away and come back. And then you get a stack of paper that has your results on it. And you may have made a mistake in your punch cards, and guess what? You do it again. What happens if the thing that the machine that reads the punch cards and into the computer breaks? You wait. During a semester, when do you suppose is most likely for that card reader to break?
Everybody's trying to use it.
When everybody's trying to use it. Excellent. Well, we've gotten away from that, right? So, on this campus, 10 or 15 years ago, we were in Grody Hall at the time, had a room like this with PCs on every table. Last week of classes, what do you suppose students were doing? Trying to do whatever they needed to do to get through the course. And there was a campus power failure. So, save often and frequently too is a good thing to learn. So, we had all these computers dead in the water. So what happened yesterday? We're so modern here, we got remote labs. What happened, Ronnie? Yesterday morning. Power went, and computers didn't automatically come on, some of them, and other things didn't happen in the lab like they went to. So, guess what? Things still happen, just like they did when I was your age. Where was I? Oh, this is, okay.